The last major topic in this section is the intermediate value theorem. So the intermediate value theorem actually has a lot of applications in Calculus 2 and Calculus 3, physics, etc. So it's kind of an important one. So suppose that you have a continuous function on the closed interval a to b, and L is a number between f of a and f of b. Then there exists at least one number c in the open interval a comma b, satisfying f of c is equal to f of L. Okay, so it sounds more complicated than it is. So there's two conditions to note. So condition number one is right here. You have to be continuous on the closed interval a to b. So that is condition number one. And then you have to have a number, L, that's between f of a and f of b. That's condition number two. So you have to have two things happening, which are pretty common things to have happen, especially with polynomials. And so that's lovely. And what it's saying is, hey, if you're continuous and you've got some number between your starting and ending values, then somewhere you must have been in the middle, or somewhere between. So you must have been equal to that between value, in other words. So let me write this down. So if the function is continuous and goes from low to high, right? Goes from a low value f of a to a high value f of b, or vice versa. Goes from low f of a to high, which is f of b, or they could be reversed, right? High to low, either way. Then it must have a middle somewhere. And that's what L is. L is that middle value. Have a middle, aka intermediate, see it now? Intermediate, middle value somewhere in that interval. Somewhere in between A and B, someplace, you must have hit the center. It's called the Goldilocks theorem, right? So one of the values is too low, one of the values is too high, and then you're looking for the one that's just right, right? So Goldilocks is a famous children's fairy tale, right? Goldilocks and the Three Bears. So if you're low on one end, high on the other, then you must have hit the middle someplace. No, this is a very powerful theorem. It's actually deceptively simple, but you have to pay close attention to what's required, because if you don't have either one of these conditions, either this one or this one, you're in trouble and you can't use it. So let me explain why. So the first part is a graph of, let's see, L is in the middle. Oops, they called it K here, but I'll call it L. Right? That'll match the graphs. So L is in the center. I have f of a up here, I have f of b down here. So I actually went from high to low, and that's fine, right? So up here is the high value, down here is the low value. No problem, right? There it is. And at some point, maybe more than one point, we must have hit the middle spot between those two. A middle spot, any middle spot. It didn't have to be that one. It could have been anything between f of a and f of b. But if you don't have a function that's continuous, then it could skip over and never be equal to the L value. So that's why condition one is so important. And obviously condition two is important, because if you're a number, L is not between f of a and f of b. If L is like way up here, then that's not going to do you any good at all, right? The whole point is that it has to be between these two values. F of a up here, f of b down here, has to be between them, and that function has to be continuous. So let me make a note. So I circled this and just said, since it's not continuous, the intermediate value theorem, IVT is how we abbreviate it, but we're lazy, so we'll call it IVT. So the intermediate value theorem will not work. It's not going to happen, right? You have to have that continuity. And it has to be on a closed interval, by the way, right there. It has to be. All right, explain why the function must have an x-intercept in the given interval. All right, that's interesting. So, and I'm just going to assume they mean using the intermediate value theorem. So I'm just going to add that. Okay, so if I'm going to use the intermediate value theorem, I have to prove, first of all, that it works. So, and yes, that's an important step. You can't just go off willy-nilly using a theorem like this. So we first need to, step one, prove that the IVT applies. Right? This is important, and you don't want to lose points for not doing it. So you have to prove that it works. So start off with condition one. Condition number one was that our function, f of x, which is this function right here, is continuous on this interval. So f of x equals x squared minus 3x minus 7 is continuous on 0, 5 because, so we have to explain why. Well, it's because this is a polynomial. If you remember several pages ago, we said all polynomials are continuous everywhere. Polynomials, sine, cosine. Here they are. They're always continuous. All polynomials are always continuous. All right, so because f of x is polynomial. Right? Polynomial, exponentials, and sine and cosine functions are the, and now arctangent ones and stuff like that are the ones that are continuous everywhere, so we don't have to worry about them. Condition number two takes a little bit more work. So I need to find f of a, which is f of 0. I need to find f of b, which is f of 5. So that'd be 0 squared minus 3 times 0 minus 7, which would be negative 7. F of 5 would be 5 squared minus 3 times 5 minus 7. So that's 25, take away 15, take away 7. So that's 10, take away 7, which is 3. Wonderful. So I have my f of a, right here. There's my f of a. There's my f of b. So I've got my low and I've got my high. But where's my middle? What's my L, my middle value? And that's where it's a little bit tricky to spot, but it's right here in this word, X-intercept. Since I want an X-intercept, I want the y to be equal to 0, which that will be my L value, right? So now you have to ask yourself, is L, which is 0, in between L equals 0 is in between. How do I put that? Let me just write that. So take these two numbers and use them, right? One's low, one's negative, one's positive. So L equals 0 is between f of 0 and f of 5. So condition 2 is met. Right here, I just proved it. Right there. All right, so step 1, I've proved that the intermediate value theorem exists, and actually that's all they wanted, right? So I'm done actually at this point. F of x equals x squared minus 3x minus 7, and this means therefore. That's what that little triangle of dots means. Therefore, f of x equals x squared minus 3x minus 7 has an x-intercept somewhere in this interval. Now notice I'm using parentheses there because it's actually within the interval. It's not going to be at 0 and 5. It can't be because this is an intermediate value theorem. It's going to have to be in between those values somewhere. So somewhere in the middle of this interval, contained within this interval, this open interval, I must have an x-intercept. Step 2 would be to find it if they asked me, but they actually didn't ask me. So step 2 would be to find the value if asked, but we were not asked. Not for this example.